So by now, I mean, we're looking on something like 30 plus years of experience with Earth orbiting satellites. And as we have now learned, Phase 3 Express is on its way out of the integration room, hopefully soon. More and more components are coming. And as we all know, all these missions, they take a long way from first conceptual design through integration up to really into orbit. I mean, the next mission has to be planned well in advance, and that's why we had this Mars kickoff meeting 2001 for P5A. And the Amsat Uk L decided that the next stop for us would be Mars. And why Mars? From our perspective, we say Mars is the next stop beyond Earth orbit. And as we heard yesterday, I mean, there are other yeah, see, and this doesn't work. The animation apparently doesn't work. The next stop beyond Earth orbit for us is Mars and not Moon. Why not Moon? I mean, we have heard yesterday that Moonlight is going to target the Moon with some penetrators. And the concept of penetrators is actually very interesting also for P5A and for Mars. I'll come to that later. But the problem with orbits around Mars are that these orbits are inherently unstable because Earth is so close. That sounds a little bit funny, but the perturbations of the Earth's gravitational field will eventually lead to an instability in all Moon orbits. I mean, this was known from the Apollo days. Apollo, in addition, mapped some mass concentrations, so-called mass cons, underneath the Moon's surface. So even if you would take away the Earth, an orbit around Moon is a little bit more difficult than any orbit around Mars. And as a matter of fact, one of the Mars exploration rovers last year did an image of a Viking orbiter, which is still in orbit around Mars now for over 30 years. So Mars orbits are really, really stable. Moon orbits are not stable, which would require us to take a lot of fuel into the Moon orbit just to keep it in the orbit. And that is something which ultimately limits the lifetime of such an orbiter in any orbit. The baseline concept for the P5A mission would be, again, the P3D spacecraft bus. We have seen this here. I mean, it's the well-known geometry. We have the hexagonal structure with about 2 meters of diameter. Launch mass would be around 650 kilograms. And plenty of space for antennas, and we will need this, as we will see later. One thing we actually need is a propulsion system. For the sake of saving money throughout the whole mission, we cannot afford to go to NASA, ESA, whatever launch authority and tell them, okay, we want a trajectory delivered by the launcher to us, which puts us on the direct course of Mars. It is just not possible because such a launch would easily cost something like in the order of 100 million euros or dollars. And so the plan is still to target the geostationary transfer orbit, the GTO, which is, let's say, the standard orbit delivered by all the commercial launchers. And from there, it's our own duty to get from Earth to Mars, and that is certainly something completely new because all the earlier Mars missions relied on the launcher that delivered them directly to Mars. So the question is, do we have enough power to go there? We have, again, here a conceptual image of the whole situation. So first of all, we are delivered, and this is of course not to scale. First of all, we are delivered in this geostationary transfer orbit, which is a long ellipse around the Earth. The business is now that we have to rotate the ellipse such that the perigee will be at the right time in the right point in space. So if we actually ignite the engine here, we will get the additional kick which carries it out to the location of Mars. And to make things even more complicated, Mars has to be there at the right time as well. And this leads us to these 26 months of period between two launch windows, planetary launch windows. And if we now crunch some numbers and stick with 650 kilograms of launch mass and the so-called ISP, that's a specific impulse which you see in the upper right, that's something like 3,000 meters per second. That is a number which tells you something about the efficiency of your engine. I mean, we are thinking here again about engines, either the 220 Newton engine which we're using for P3E or something very similar to the 400 Newton engine we were using on Amsat Uk 40. And if you just balance the numbers between the dry mass, you put a little bit more fuel in, and therefore you have to reduce your payload, or you increase your payload, you have to decrease the fuel amount a little bit. You can play around with the delta V numbers, and you have your delta V numbers in the order of 2.25 kilometers per second to 3 kilometers per second. And this sound to most of us certainly is a little bit on the low side. However, one has to take into account that if we are in this geostationary transfer orbit, we already are close to 10 kilometers a second in perigee. And escape trajectory requires something like 11.2, 11.5. So for Earth departure, there is not much more we need to actually get rid or get out of the Earth gravitational field. Just for curiosity, I calculated the numbers for Amsat Uk 40, and maybe James can correct me if I'm wrong, because he knows these numbers certainly much more better than I do. I think this burn, which in the end resulted in this little explosion, was programmed for 3 minutes. It actually lasted something like 6 minutes. And if this engine would have fired for 18 minutes, which is well in the capability of the engine because we had fuel on board for something like 30 minutes, we would have left Earth orbit already with Amsat Uk 40. And this is certainly something which would not have been planned for this at all. As you see here, I mean, the fuel tanks are rather big, but there's no direct reason not to enlarge them a little bit bigger. I mean, you can decrease the payload base a little bit more and size up the engine tanks a little bit more, and therefore increase your delta V and your propulsion capability. So communications, of course, is a whole different story. I mean, we have been dealing with maximum ranges about 60,000 kilometers, 70,000 kilometers in terms of AMSAT. Going interplanetary was something unheard of until the early 2000s. And Amsat Uk got hold on this 20-meter dish in Bochum, which at that time was an industrial monument, let's say. It was out of function. And I think 1 or 2 years before, this radome, which is actually just held by the air pressure inside, it collapsed and it had to be replaced. So with lot of private efforts and volunteer efforts and man hours, this was done. This was brought back into service, and by now we have this antenna more or less for ourselves in terms of operation. In Friedrichshafen, I have been asked that, or the question was, all this operation, all this power, the heating, that must cost an enormous lot of money to Amsat Uk. The truth is that just keeping the thing alive doesn't cost Amsat Uk a single penny, because as this is still an industrial monument, it is funded by the country of North Rhine-Westphalia. And they are taking care of keeping the thing alive, preventing that it has enough, or preventing that you have, for instance, in winter, if you have a lot of snow on the radome, the radome can take the weight, so you have to crank up the heating. And this is something which is really expensive, and the country is taking care of this. So all we have to, let's say, pay for is the equipment we're going to install. And this makes things a lot more easier for Amsat Uk. And I mean, we have worked over the last couple of years extensively on improving the setup every time a little bit more, and make it more sensitive, make it more accurate. And up to now, best achievement, let's say, was the now well-known reception of the Voyager 1 space probe. In 2006, it was the 14.7 billion kilometer distance. In the last 2 years, we have improved the setup even more. So by now, it really takes us a few settings and flipping switches on the dashboard, and we can basically receive Voyager within a few minutes. And all of this preparation is now gone, everything is in place. And actually during the AMSAT symposium in, when was it, end of May I think we went after dinner. We looked at the watches and say, okay, Voyager's coming up. So we finished the dinner, went over to the control room, flipped all the switches, and said, okay, here it is. That's basically it. So it's all of this is now very, very reliable, and that is a key point if you want to use this for something which is really then critical, mission critical. We even sent out an SWL report to the Voyager flight team, and well, we got it confirmed.
Via the bureau?
No, direct. Stuff like this you don't send via the bureau now. Okay, scientific payload. Although, I mean, a couple of chaps would be just really interested in having a beacon, an amateur radio beacon around Mars. I mean, that's certainly not enough. You can and should carry some scientific payload with you, and depending on the actual launch dates, we're talking here about 60 to 65 kilos of scientific payload. This structure with this propulsion capability is able to carry with him. And one idea of many ideas I'm going to present now, I'm only a few. One idea would be a tomographic survey of the Mars ionosphere with radio occultation. That is something which NASA and ESA have been doing for years now with their orbiters. However, this is heavily dependent on the availability of the Deep Space Network, because they do this scanning. It's basically comparable if you have a broken arm and go to your doctor, your arm is scanned basically by shining X-ray through your arm. And what is done here is you shine radio frequencies through the ionosphere and just measure how much gets through. And as I said, if NASA and ESA are doing this, they have to do this with a transmitter in, let's say, Mars Express, and the receiver is on ground here on Earth. And while doing this, basically, the antenna is blocked for anything else. And that is something which they're not very keen on. So if, let's say, P5A would be able to eject a couple of transmitters, small transmitters, in Mars orbit, for instance, CubeSats, for instance, from a P-pod, this would be quite an interesting situation, because assume now you have the P5A, let's say, mothership, and distributed over the orbit some 3, 4, 5 other CubeSats which are all transmitting on different frequencies. You can have basically a survey of Mars ionosphere in situ, locally, on different frequencies, and that is certainly something neither NASA nor ESA is capable of. We have said this earlier, Peter has mentioned it, the Mars exploration rovers, the Phoenix lander, none of them are communicating directly to Earth. They all use the so-called Proximity 1 protocol in the 70 centimeters band to uplink the data to Mars Odyssey. And actually, ESA is planning this ExoMars for 2014, but they are not so sure how to get the data back. Sounds a little bit ridiculous, but it is a real problem apparently, because if they are focusing on ExoMars, they cannot, let's say, focus on a telecommunications orbiter which is capable of transmitting data back. So they're really interested in having at least a backup, maybe not the prime data relay, but a backup data relay on Amsat P5A. And here comes the flexibility of SDX into play. I mean, the software-defined radio or the software-defined transponder, something you can actually reprogram on the fly. You can incorporate new protocols, you can incorporate new coding schemes. So this can be adapted to many, let's say, customers on Mars. So our time planning, as Peter already mentioned, this can and most likely will shift a little bit. The launch of P3E is currently foreseen in 2009. The project start of P5A is currently listed for 2008. It is, let's be honest, it's only dependent on the money. As soon as the money is there, we can give this an official go. P5A would be then launched either late 2010 or early 2011. But everything following this one, including this item itself, is then depending on how fast can we construct this. We can pull a lot of heritage from P3D because the structure is the same, the engine might be quite the same. And if this is shifting, it's shifting always by 26 months. That's its planetary window. So, where comes amateur radio into play? We have the 20-meter dish in Bochum, and I have a 60-centimeter dish at home. So, question, is this sufficient? Does it work? I mean, it says here right now 2.4 gigahertz, because that was my Mode S antenna for Oscar 40. But can this work on 10.4 gigahertz, which is the prime downlink for P5A? So the main number you're interested in is the so-called path loss. And the path loss is easily scalable. You have a 60 dB penalty every time you double the frequency, and you have a 60 dB penalty every time you double the distance. So you start doubling, and adding 6 dBs, and so on. And just for the sake of simplicity, we assume one astronomical unit, that's just the distance between Earth and the Sun, and 10.4 gigahertz as the prime downlink frequency, and we arrive at a path loss of minus 276 dBs. And then I compared this to EME on 10 gigahertz, and I ended up with minus 295. So actually EME should be something like 20 dBs worse than this Mars link. And I scratched my head and said, well, can this be? Is EME really 20 dB worse? Or in other terms, is Mars 20 dB easier than EME on 10 gigs? I was quite confident that it's minus 276 dB number, the upper one, because we have been using these formulas now for years to predict signal strengths from Voyager, from all the Mars probes and everything. But I wasn't so confident about the 295, so I talked to some EME veterans in Switzerland, and they say, oh yeah, 295, that's the right ballpark. So I conclude, yes, it is actually 20 dB easier to get a signal from Mars than making an EME contact on 10 gigahertz. And for those who have been here the last few years, they know how easy, let's say, it is to receive Mars signals with a 1 meter dish. Freddy has done these demonstrations here in the last couple of years. He has done it at the ham radio again. Interestingly, that's a nice side remark. You might notice this odd subreflector here with the Amsat sticker. I mean, this one was still a foam prototype. I mean, by now he has a milk prototype. And actually, he already determined that this is about 2 dB improvement over, let's say, a standard dish of the same size. So the antenna efficiency has gone up to something certainly like above 80%. And that is something to do with the special shape of the antenna and the subreflector. And actually, it's the same antenna design which is used by NASA on the Mars Reconnaissance Orbiter. So they should know what they're doing. At least I suppose so. So again, if we start crunching the numbers, we can assume that on the transmitter side, we will have the whole front of P5A covered with a big parabolic dish. We assume this 80% of gain or efficiency, which is achievable as we know now, and we end up with close to 46 dBi of antenna gain. If we assume now that we have a TWT of 100 watts of power and the path loss, which I mentioned earlier, of minus 276 dBs, you can calculate how much signal is arriving at Earth after 1 astronomical unit of distance. Now, I take my 60 centimeter receiver antenna. It is only 60% efficient because I built it in my room. It's bad. So you end up with only 34 dBs of gain, and you end up with something like minus 146 dBms. So how much is it? This is a lot. So you compare this to noise. On 10.4 gigs, what is a reasonably achievable system temperature or noise figure of your receiver? Maybe 110 kelvins, 1.4 dBs. I'm pretty sure people can do better by now. I mean, there exist very low noise preamps and very good converters, but this is a conservative number. When I assume a bandwidth of 400 hertz, which is really matched now for the Oscar 40 telemetry, that's that beacon, that PSK beacon, and we use forward error correction. If you just add up all the numbers with the Boltzmann equation for noise, you end up with something like minus 152. And if you compare this to the signal power you have something like 6 dBs of signal over noise, which is quite a lot, because the forward error correction of Oscar 40 should work down to something like 2 to 3 dBs. So what we see here, Amsat Oscar 40, like telemetry, could be decodable with a 60 centimeter dish, that's this size, over a distance of 1 astronomical unit. That's 150 million kilometers. And if you go all the way to the limit, then the 60 centimeter dish would even work to, let's say, 1.4 AU. This is not quite the whole story, because depending on where Earth and Mars are on their orbits, the maximum distance can be something like 2.5 astronomical units. So that is actually the worst case, which is plotted here right now, if you have to go all the way across the solar system. And this is, as I said, 2.5 AUs. So you have to beef up your system a little bit, but not much. 1.2 meters. That's all you need. And 1.2 meters is quite, let's say, good antenna size, which you can put on your roof. You can equip with antenna rotators and everything without bothering too much about wind load. What is also interesting is, if you want to stick for the 60 centimeter dish for the sake of simplicity, mobility, whatever, how long can I really do receiving with such an antenna during this 26 months period of the distances between Earth and Mars? And if you plot this, you will see that you have about, well, 9 months out of the 26 months, which are perfectly decodable with a 60 centimeter dish. And if you really stress it to the limits, so you wait for the, let's say, closest approach here, I mean, by theory, a 30 centimeter dish should do the job. Maybe for 1 week only, or let's say 4 weeks only, but I think this would be real good demonstration. Let's assume you're here in Surrey or at Dayton at the Hamvention, and you have a 30 centimeter dish and say, I'm receiving Mars telemetry right now. I mean, they will all think you're stupid, but if it works, that's fine. So if I've now just proven that a 60 centimeter or 120 centimeter dish is okay, why do we need the 20 meter dish in Bochum? Some might ask, and there are 2 reasons for this. One reason is you might want to increase your data rate a little bit over this 400 bits PSK, because if you really want to download scientific data with 400 bits, it's a little bit tough. Especially if you are going to ESA and say, oh, you have ExoMars, you have megabytes of data you want to download from your drillers and meteorological data, we can only offer you 400 bits per second. I mean, they will say, oh, this is too little. So if you want to have a high bandwidth, you have more noise. If you have more noise, you need more signal. If you need more signal, you need a larger antenna. That's point number 1. And point number 2 is, we have to make sure that emergency communications will work always with P5A, especially if P5A is not pointed to Earth for some reason. Maybe it goes into safe mode and just points its solar panels to the sun, which does not necessarily mean you're pointed to Earth anymore. And then you have to rely on, let's say, backup communications over the Omni antennas. They will have very little gain, so all the gain has to be made up by the ground station. And that is where the 20 meter dish kicks in. So if a small dish is fine for, let's say, standard operation, one might ask, well, is it the other way easy as well? Can I transmit actually to P5A with my own signals? And well, principally, yes. If you are going to the legal limit, at least in Germany, 75 watts, PEP is the legal limit for 10 gigahertz, and you take a 100 centimeter dish, this might do the job. Practically, it's a little bit difficult because the round trip time for any effect you have requested can be up to 45 minutes. So assuming you want to download a picture, which you have taken on Mars, you send, I want to have picture number 35 out of the gallery, then you have 45 minutes to wait until the picture is actually starting to download. I'm not saying that the download has actually finished. So that is really annoying. What is really, really crucial, any uplink like this should not interfere with the command operations, because it might be that P5A is in a really life-critical state, and then the last thing what you want is that somebody starts downloading a picture. And third point, maybe a 75-watt power amplifier 10.4 is not very common, although they start appearing now on the market because everybody's going to transistorized power amplifiers, and all the traveling wave tubes are now appearing. So I leave this point open for the future. I'm certainly not deciding right now whether this will be open, let's say, for general uplink or not. So if it's only receiving, which will be the prime participation of radio amateurs to P5A, what can this contribute? And having distributed receiving stations for the telemetry, I mean, Delphi C3 was the perfect example how well this can work. They have distributed the decoding software among the radio amateur communities. They had tremendous success in getting, how many? I mean, thousands of telemetry blocks back. And the same could be the case with P5A. I mean, you have the Kepler elements of Mars. Certainly you or we as mission control have to provide some kind of tracking software, because tracking of an interplanetary probe is a little bit different than tracking a satellite around the Earth. But still, this is some very valuable data which can be delivered by basically every ham which has a 120-meter dish or a 60-centimeter dish. And it's even possible that these receiving stations, if worked in a synchronized manner, can contribute to ranging and navigation, collecting navigation data for P5A. I mean, we have been thinking about whether it's possible to do a worldwide synchronization of these receive stations via GPS, and achieving timing resolutions or achieving accurate timing in the order of, let's say, 20, 30 nanoseconds or even less is not impossible by now with modern GPS timing receivers. And if you think about it and crunch the numbers again, it should be possible to achieve a navigational precision of roughly 50 kilometers, give or take, over a distance of 1 astronomical unit. So to summarize, a little bit ahead in time, but that's quite nice, so we are open for questions. Amsat UL, we are planning the first private mission, and this has to be stressed out, especially if you're going to funding agencies. This could be the first private mission to Mars for the 2010-2012 timeframe. We have validated the technologies already on Amsat Oscar 40. Some of the technologies we have not validated yet will fly on P3E, the coherent transponder, which was presented by Peter already. It's the best example for this. We do not need oversized antennas for reception, at least if everything is going well. 20-meter dish is for emergency communications, it's a backup, but a standard 400-bit telemetry will be perfectly decodable with radio amateur sized antennas. So my conclusion is really that any radio amateur which is willing to do so can participate in P5A. And well, that's it. Thanks a lot for your attention.